Welcome to AI Podcast. I'm Daniel.
And I'm Maya. Today we're talking about a new EMNLP paper called Code Like Humans, which sounds ambitious. What's the punchline, Daniel?
The punchline is simple. The authors built a 4-step, multi-agent workflow that tries to code medical notes the way human coders do. Analyze the note, look up candidates in the ICD alphabetical index, validate them in the tabular hierarchy and guidelines, then reconcile the final list. It covers the full ICD-10 space, all 70,000-plus codes, and it's especially good on rare diagnoses. Classic discriminative systems still win on common codes, so the message is, assist humans, don't replace them.
So it's not another, let's fine-tune one big model and hope for the best. It's more like mimicking the actual job.
Exactly. Think of it like navigating a city. Most models try to memorize every street. This system grabs the official road atlas and the rules of the road, then plans a route step by step.
Nice. Who's behind it?
A team led by Andreas Motzfeldt, with Anna Rogers and colleagues from Corti and the IT University of Denmark, plus the University of Copenhagen.
All right, set the stage. What makes medical coding so hard for machines?
3 big headaches. First, the label space is huge. ICD-10-CM has more than 70,000 diagnosis codes, and most academic benchmarks carve that down to a tiny subset. Second, the distribution is brutally imbalanced. Common codes appear everywhere. Many legitimate codes are rare, which makes models shy away from them. Third, notes are long and messy. You're dealing with abbreviations, histories, medications, and assertions like ruled out versus confirmed.
And previous systems?
The strongest ones are discriminative classifiers trained specifically for coding. They do great when the right answer is common in the training data, but they usually restrict the label set to whatever codes show up in a data set like Mimic. That's convenient for research and not quite how hospitals work.
Right, because a hospital doesn't say, we only use our top 1,000 codes. So how does Code Like Humans actually operate?
4 agents, same backbone model, different roles. First, an evidence extractor scans the note to surface code-worthy snippets. Second, an index navigator takes those snippets and looks up terms in the official ICD alphabetical index, so it can handle synonyms and eponyms. Third, a tabular validator checks the ICD hierarchy and chapter-specific rules, narrowing to the most specific valid codes. Fourth, a code reconciler applies ordering and exclusion notes to produce the final list.
Give me a concrete example. Let's say the note mentions sepsis.
Great example. The index has entries for sepsis in multiple contexts, like post-procedural or due to an infection like anthrax. The navigator proposes those candidates, the validator checks the tabular list and guidelines to see which contexts fit the evidence, and the reconciler ensures you don't output mutually exclusive codes or miss required companions.
Got it. What did they test this on?
2 main resources. They fine-tune and sanity check with the common Mimic 3 split, but the more realistic evaluation is MDACE, which links ICD codes to exact evidence spans in real notes. That span-level supervision lets them judge not just whether a code is right, but whether the system found supporting text that a human would agree with.
Metrics?
The usual F1 scores, both micro and macro, plus exact match of the whole code list. Quick reminder, micro F1 is dominated by frequent labels. Macro F1 weights all labels equally, so it reveals how you do on rare codes.
And what did the scoreboard say?
In the restricted label setting, about 1,000 codes to match older work, the old discriminative baseline still edges out the new system on micro F1, meaning it's better on the common stuff. But Code Like Humans pulls ahead on macro F1, meaning it's stronger on rare codes. Then they open the gates and let the agents operate over the entire ICD-10 universe. Performance dips, as you'd expect, but it's the first rigorous demonstration that an automated system can even run across all codes, not just a curated slice.
That's important. Hospitals live in the open set world. Did they analyze what each agent contributes?
They did. As the pipeline progresses, precision climbs. The index navigator has broad recall but is noisy. The tabular validator becomes more selective, and the code reconciler is the most precise while keeping recall healthy. It matches the human workflow. Cast a wide net, then tighten.
Any blind spots?
Yes, and this is one of my favorite parts. They slice performance by ICD chapters and find weak spots in mental and behavioral disorders and in the Z codes, things like social factors and administrative context. The misses often trace back to abbreviations such as history of CVA or cues like DNR and medication mentions. Those aren't diseases, but they change how a disease should be coded. Humans key off that context. Models still struggle to interpret it consistently.
So the system needs to be better at reading between the lines, not just the lines. What about the effect of throwing more candidates at it?
Classic trade-off. As the candidate set grows, both the validator and the reconciler find the job harder. However, the reconciler, because it's applying firm rules, degrades more gracefully. The team shows a neat mitigation. Curate the context you feed in. Adding short code descriptions helps. Adding chapter-specific guidelines helps even more. It's like giving the agent a condensed rulebook right when it needs it.
I love that. Give the model just enough structure to avoid wandering. Did they try anything on the reasoning side?
Yes. They compare structured decoding to what they call thinking-enabled generation. The latter lets the model take a free-form reasoning pass before producing a constrained answer. That consistently improves accuracy, especially when the candidate list is big and the context is long.
And fine-tuning large language models directly for coding. Any luck there?
Straight fine-tuning of a generative model underperforms the discriminative baseline. But when they bolt on label-wise attention, so the model explicitly learns to attend to each candidate label, the gap closes on the standard Mimic 3 benchmark. That's a nice signal that some of the discriminative magic can be ported over, but it doesn't replace the multi-agent design that makes open-set coding workable.
Okay, let me sanity check the big picture. The system is strongest on rare codes, can operate across the full ICD-10 label space, and benefits from adding official descriptions and guidelines into the prompt context. But on very common codes, the more traditional classifiers remain tough to beat.
Exactly, and the authors are very clear about deployment. Today, this is a co-pilot. It can surface evidence, propose candidates, and apply rules at scale, but final judgment should rest with a human coder.
Let's talk about caveats. Any red flags on data, sample sizes, or reproducibility?
A few to keep in mind. MDACE is high quality, but it's still a relatively small set of charts compared to the real world, and it reflects one hospital system's documentation habits. There's no public data set that truly exercises all 70,000 codes, so coverage is hard to measure comprehensively. Also, pipeline systems can propagate early mistakes downstream. They note a self-refinement loop as a promising fix. And while much of the stack is open weight and the code is released, some runs used closed models in HIPAA-compliant setups, which not everyone can replicate exactly.
Right. So it's transparent by research standards, but not push-button reproducible for every lab. What about the classic concern with models that explain their answers?
They lean on reasoning-style decoding for accuracy, but they warn that the reasoning traces shouldn't be treated as faithful explanations. In a clinical audit, you'd want the span-level evidence and the ICD guideline references, not the model's inner monologue.
Practical question. If I'm a hospital coding director, how do I picture using this?
Picture a sidebar in the encoder's workstation. The system highlights quoted snippets from the note, shows the alphabetical index hits, lists a small set of validated candidates with short descriptions and relevant chapter guidance, and then proposes an ordered code list. A coder can accept, tweak, or reject, and the system can rerun with that feedback. Over time, that feedback tunes the evidence extractor and the reconciliation logic.
And research directions?
3 that stood out. First, better evidence extraction with entity and assertion detection, so the pipeline only passes on eligible facts like confirmed pneumonia with laterality and acuity. Second, smarter index navigation using label-wise alignment to handle synonyms and eponyms. Third, broader public benchmarks that link codes to evidence spans across specialties, especially mental health and social factors where the model underperforms.
I like that the future work is very actionable. It's not, let's wait for a bigger model. It's, let's wire in the tools humans already use. Before we wrap, can you give me the 30-second takeaway?
Sure. If you want machines to code like humans, make them use the human playbook. This paper shows that an agentic workflow grounded in the ICD index, the tabular hierarchy, and the official guidelines can cover the full label space and rescue rare codes, which is where money and safety often hinge. Discriminative classifiers still rule the common cases, so the winning near-term setup is a co-pilot that combines both strengths and keeps humans in the loop.
That's clear, and honestly, it feels like a more respectful way to bring AI into clinical operations. Use it to reduce the grind and the misses, not to bulldoze expert judgment.
Well said. That's all for this episode of AI Podcast.
If you enjoyed the discussion, share it with a colleague who lives in ICD-10 land. See you next time.